Hello everyone and welcome to this next lecture on Python Power Electronics, and in this lecture we're going to start with closed loop control. So first and foremost I'll go over to my directory, and this is the simulation folder, or rather the folder with all the simulation files. And as you can see, we started off with PWM concept. We then went on to show how a filter connected to this inverter can result in a sinusoidal voltage. I had left inverter voltages for a practice, that is for self work, and finally I showed how inverter voltages with a three-phase inverter bridge, or rather three-phase DC to AC converter bridge with 6 switches and 6 anti-parallel diodes can result in a three-phase sinusoidal waveform when it is connected with a three-phase LC filter again. So now that this is done, we are now going to go to closed loop control. So there are two folders here: closed loop current control and closed loop voltage control. So let's go and start with current control, and I'll show you why. So to begin with, let's start looking through the circuits. Now here you will see there are a lot of circuits. Okay, so to begin with, there is, now always look for circuits as _CSV with their _params.csv. So the first one is inverter bridge.csv. So let's open this one. It's taking some time to load. Yeah, okay, finally. So this inverter bridge.csv is exactly the same three-phase DC to AC converter that I showed before. Alright, one DC source, 3 legs, each leg with 2 switches, an upper switch and a lower switch, and each switch with its anti-parallel diode. Alright, we take the midpoint of the 3 legs out as 3 phases. Alright, so far so good. Now what comes after this? We are going to connect to that an inverter filter. Again, this is exactly the same as the previous case. It just didn't load. Okay, here you see I am connecting the inductor capacitor, that is, there are 3-phase inductors, there is a jump label, and there is a star connected capacitor bank. So this forms a 3-phase LC filter, and at the output there is an inductor. Now this inductor, if you want, you can just get rid of it because it's a single UPS. You don't really need it. It's multiple UPS, then you do need it, but for now you can get rid of it. It's up to you. And finally, these are output connectors. So let's go to the output. So in the previous case, all I was doing was measuring the voltage output. Alright, that's all I was doing. There was an inverter output measure.csv. Here I am actually connecting a 3-phase inductor RL load, resistor inductive load, across the output of the UPS. Alright, and I'm measuring the current through them. So now there's one last one, and I've called it bus connect. Actually you don't really need it in this case, but I've still put it because for the sake of expandability later. Alright, this merely connects these two, alright, and it measures this voltage. Again, like I said, this is really, in this particular simulation case, you could skip it if you want, but still you have to add it because otherwise it won't work. So basically this file just is a 3-phase feeder. That is, it's a very small resistor. I call it con2a. Basically it means resistance of a connector, and I'm measuring the voltage across it. So the way it would work is, in any power system you would have feeders, and at all feeders you usually have a voltage measurement. You have sensors, you have current sensors, voltage sensors. So this kind of mimics that. That is, at the output of the UPS you have a feeder, and in the feeder you are measuring the voltage and you are measuring the current going through the feeder. So now what are we trying to do? So far up till now we have just provided a modulation signal to this inverter bridge, alright, any arbitrary modulation signal, and we have observed the output. When I say the output, we have observed the output across, usually in the previous case at load we measured the voltage across this load. Now this is called open loop. Why? Because you are setting an arbitrary input and you are not measuring the output voltage and trying to regulate it. Alright, you're just giving some input, seeing the output. This is called open loop. But what we are going to do now is we are now going to start closing the loop. So in a UPS, what you want to do, the ultimate objective is to regulate the output voltages. So rather you would regulate, either you would regulate the voltages across these filter capacitors, or you would regulate the voltage that this feeder sees. Alright, this feeder again is voltmeters connected in a star. So if you can regulate the voltages that these feeders see, you are regulating the voltage of the system. And that's what what we eventually need to do. The problem is we can't go there directly, and I'll tell you why. Let's go over to the filter schematic. Now what we have is this inductor is directly at the output of the bridge. Alright, if you check, this jump inverter phase A is at the midpoint of this switch, of this leg, that is phase A leg. And finally this inductor is connected to this star connect capacitor bank. What we want is to regulate the voltage across this and eventually regulate the voltage across the system. But we have this inductor coming in between. Okay, now there are certain advanced control strategies, alright, things like deadbeat control, pole shift control, and certain other things where they attempt to regulate the voltage across this filter capacitor directly without ever caring what the current through this branch is. Alright, there are certain advanced strategies, but in almost every strategy that you will find, it's a two-stage process. Why? Because when you change the modulation signal, the first thing that will change is the current through this inductor. Alright, and the current through this inductor will change because the voltage across the bridge changes, and the difference between the voltage across this bridge and the voltage across the capacitor bank will decide the current through the inductor. Okay, now as you change this inverter output voltage, you are changing the current, and that in turn results in this capacitor voltage changing. So if the way we are going to do this control is, we are going to first regulate this inverter first we are going to say to regulate the capacitor voltage, which is the output voltage of the UPS, we need to first regulate the current output of the inverter. Okay, so in this lecture I'm going to focus on that. I'm going to focus on how you can regulate the inductor, the current through this inductor, to some desired value. Alright, and in the next lecture I'll tell you how we can set this desired value according to the output voltage of the UPS. So anyway, let's get started with some simulations. That's most important. So first I will go into my virtual environment directory, and as always, first thing you should do is activate the environment. So let's do a little test, python -v, we are okay. So then after that we can go into the simulator directory. Run server. So usually I don't expect this to fail because I've been using it over and over again, and usually the server, it might have certain problems at the startup, but once it's up and going, it usually always works. So let's go, paste it and press enter, and this is our circuit simulator. So we stopped here, single UPS 3-phase output with LC filter. Okay, that is in open loop. Now we're going to create a new simulation. Let's call this single UPS inverter output current control. Okay, so we are controlling the output current of the inverter. So let's do this. Let's now go over and get the path. Properties, select all, and paste it. Save. So it's all working. Let's go back to let's add the circuits. So as I said, we have 4 circuits to add, and those are the 4 that I showed you. Closed loop current control, most important, inverter bridge, this is the starting. After that comes inverter filter. After that comes inverter 3-phase load. And the last is bus connect. And we should call this feeder, because that's what it is. It's basically a feeder. So now that we've done this, let's process the circuit schematics. And let's go down, check the result, and the circuits do not have any detectable error, so we can go back, no problem. So we are ready to go. Let's edit the circuit parameters and let's start adding components. As usual, we will just upload the parameter spreadsheet. So let's look at, first one is bus connect. So bus connect parameters. And yeah, they have updated. Back to circuit list. Inverter 1 bridge. Upload the circuit. Inverter 1 bridge underscore parameters. And you see the parameters have changed. Inverter filter, and let's add inverter filter underscore parameters. And yeah, parameters have changed. And finally 3-phase load. So then there's upload file, choose the file, 3-phase load underscore parameters, upload it. And this is done. Let's go back to the circuit list. So now we are done with this. Now it's time to add a control. Now to add control, I'm going to go back to the directory and show you what are the control files. Or rather, you know what, let's go over to Atom. let's go to Atom, let's expand the file, and let's look at closed loop current control. Now let's look at the pi files. So there's inverter1.pi, current.pi, and as you can guess, that's the current controller. There's inverter1 modulator.pi, as you can guess, that's a pulse width modulator, and there's one other weird little file. Let's open that. This is called PLL. Now, in reverse order, PLL, to know about PLL, what you can do is you can just go over to my site and let me Google Python Power Electronics. Well, it just comes up. So at pythonpowerelectronics.com, you can go to tutorials and you can look at this first tutorial called phase lock loop. Okay, in this I have provided a detailed report along with an actual PDF file. Alright, so I would strongly suggest that you take some time to read it, because this tells you about the entire concept of PLL, DQ control, everything else. Alright, and this exact implementation is what is there in this particular circuit. So I won't go into the details now, but what you need to understand is this PLL in this case is not really that necessary, but I have done it just for you to be able to verify whether the output frequency is what we want and the output voltage is what we want. Okay, these are the voltages and we can plot them later. Now, inverter modulator.pi. Okay, now before it's exactly the same as before, there's only one change. That change is that the modulation signals before were just arbitrary sinusoids. Now they are not arbitrary sinusoids, they are some very strange variables. Inverter1 control underscore NA. To know about these variables, let's go over to this one. And you see that these variables are set here in this file. Alright. So what I'm doing is I'm calculating the modulation signal in this control function, control file, assigning it to these variables. These variables of type are of type variable storage, so they can be exchanged between files, and because they can be exchanged between files, they can also be accessed in inverter modulator.pi. Alright, so now question is, what's happening here? Let's take a little bit of a time to go through. What I'm trying to say is I'm not looking at any different kind of frequency. I'm assuming it's a 60 Hertz, typical North American, and I am setting a PI controller. Okay, these PI controllers I've tuned a little. You are welcome to tune it even further. And what I am doing is this: I am using this frequency to generate a phase angle. Simple integration. After generating the phase angle, I am doing something called as DQ transformation, or rather ABC to DQ. Now, just a little bit of theory here again. Let's go back to this file. Actually, I closed the report. I need that. So let's have a look at this. Basically, what we do is we want the angle. In general, we want the angle. And when you want the angle, what we want is we want another reference frame. That, see, this is the concept of phasors and reference frames. A sinusoid is nothing but a phasor that's rotating and whose projection on some horizontal plane is measured. So like for example, this case, this is a phasor V. The projection on this horizontal plane is Vm cos omega t, because if this is rotating with the angular frequency omega. As it rotates, its projection keeps changing, and this projection forms a cosinusoid. Okay, this is basically the concept of a cosinusoid, and this is how phasors are. Now the problem is this: when you have a sinusoid, alright, in a stationary reference frame, okay, if your reference frame is stationary, if you have a phasor, you get a sinusoid, which is what our AC signals are. Our AC signals are sinusoids, and those sinusoids can be represented as such phasors. But the problem is, this reference that we have, frame of reference, does not have to be stationary. Okay, the default frame of reference is stationary, but you can always have a frame of reference that also rotates. Okay, an example is this. Let's say you have one of those car races or whatever, right? Usually you will have another, or rather you will, in many of these races you will have another pilot that goes alongside the lead runner. Why? Because when you go alongside the lead runner, you are running at the same speed, and when you are running at the same speed, that lead runner appears to be at the same speed, stationary. It's like, let's say you're sitting in a train, right? A train that's moving. Now there's another train that pulls up next to you. You might actually think that the train is stationary with respect to you, but it's not stationary. You're moving, that train's moving. It's just because if you're both moving at almost the same speed, you get the feeling that that train is stationary. And that's the concept of a rotating reference frame. When you rotate the reference frame at exactly the same frequency as that of as your phasor, the phasor becomes a DC component because it's now almost stationary. Alright, and that's the concept of PLL. I can't talk more about this. You can read this here. Now, what we're going to do here is we do this thing called DQ transformation. So you can read that paper and you can figure out what I've done here. But this is exactly that. I'm transforming three phase sinusoids to D and Q variables in the synchronous reference frame, and these variables are constant DC values. To these constant DC values, I am now applying my PI controller. I'm taking the error, integrating, adding the proportion constant, and taking the PI controller. This output is my modulation signal, but in the DQ domain. This is again reconverted back to the ABC domain. It's just the inverse process, and this is applied to the pulse width modulator. So this is the concept of the controls here. So let's go back and let's add these three files. So the first file, of course, will be inverter current con.py current controller. And then after that we can add modulator, and after that we can add PLN. We can add PLN.py. So let's just call this PLN. Now that this is done, let's configure it. Inverter con.py inverter current con underscore desk. So as usual, we just upload the descriptors. And the files, the database is updated. Let's go back to the main page and let's now configure the next file, inverter modulator.py. This is underscore desk.csv. And you see now these update variables are also updated. And finally this configure PLL descriptor. Upload this file. And this way the database is updated. So let's go back to the main page. So now that we're done with this, we are more or less done. We can just view the output. So I'm going to click on the run button. And you see he is running, but as always go over to the terminal and check if there is any cryptic error. No, there isn't. It's okay. So it is really running. So now that we are done with this, let's add a plot, at least just to see whether it's really running or not. So let's, as always, we'll call this inverter output currents. Okay, let's plot the first variables to plot are usually the variables that you're most interested in. Now to know what you're interested in, let's go over to the circuit file. Inverter filter.csv. We are trying to regulate the output of the inverter bridge, that is this one, the current through this inductor. And these are inverter 1 filter A, filter B, filter C, okay, ammeters. So let's go plot these. Ammeter inverter 1 filter A, I shall call this IA. Ammeter filter B, IB. Inverter filter C, IC. So we are done. Let's click on done. And let's plot this. It has done something, so let's go to the folder and let's see what it has done. So we're getting some very weird waveforms, but most important, like I said, what you have to be worried of is if everything is 0, alright, or if everything is 10 raised to minus 9, then it's a problem. The other problem is if everything is 10 raised to 37, then it's a problem because now you have instability. So these two are the extreme cases that you have to be worried of right away. Something like this, even though it looks weird, is actually promising that it's probably working. Alright, so let's stop for a while. So the best way to do this is now, it'll take some time to run, and usually most of these kind of closed loop power electronic stimulations typically take time to run. They could take like sometimes half an hour or whatever, I don't know, depends on how big it is. I have run some huge microgrid simulations for like a couple of days even. Okay, so I'm going to pause this video and I'm going to come back in a short while once the simulation is run. Alright, so stay tuned and don't run away. So we are back again. It's been running for a while, so let me now check the plot again. Let me click on the plot button, same old plot. So it has been running for a while because that shows how long it took to generate the plot. And let's open this file. Yeah, so as you can see, it has now run for close to 0.4 seconds, or rather a time duration of 0.4 seconds. It's been running for like close to half an hour to 45 minutes. Now it doesn't look like much. Alright, we wanted something which is like a regulated current waveform, and we see something very different. So simplest thing to do in this case is let's zoom in. So let's zoom in one cycle. That's 0.35 to 0.37. My computer is hanging. This is what happens when you deal with huge graphics. It just hangs. So anyway, so I had chosen 0.35 and 0.37. Yeah, that's close to where we were towards the end, and it's one cycle. Alright, so this is now much clearer. Alright, now you see here, these are essentially three balanced currents. So there's blue line which is phase A, there's orange line which is phase B, and there's green line which is phase C. So well, you can look at it this way: the blue line here, the orange line here, the green line here. So the orange waveform, that's phase B, lags behind the blue waveform, that's phase A, by 120 degrees, and similarly phase C, which is the green line, lags behind phase B, which is the orange line, by 120 degrees. So this is indeed a three-phase balanced voltage. So now what is all this? Alright, interesting question. So let's go zoom in. Let's zoom in between 0.355 and let's say 0.3625. 0.355 and 0.3625. Because it's just interesting to know what all that is. Right? We see a really thick waveform. So let's plot this. And this shows you exactly what it is. So you see what's happening here. These currents now have the switching frequency ripple that is produced because of the high frequency switching of the inverter. Alright, the output voltage of the inverter is a switched output voltage, is a 5 kilohertz switched output voltage. It contains 5 kilohertz. Alright, now we are using these inductor capacitor filters to filter it out, but the inductor will still contain those high frequency harmonics. We cannot get rid of them. Alright, so now the question is, if this is how the inductor current is, how would the filter current, how would the capacitor currents be? So let's plot those. I can't believe my computer is this slow. And I'm using Linux. Wow. Okay, so let's now plot. Not this one. Let's go to the filter. And let's plot these three capacitor voltages. That's V inverter filt B, filt C. Okay, so let's go add those. Add plot. Let's call those filter capacitor voltage. Start plot. Let's add voltmeter inverter filt A. Let's call this VA. Then there is save waveform. Now that's filt C. I need filt B. No, it's ammeter. Filt B. Filt C. So let's plot this. Because up till now I have only plotted the output voltage. I have never plotted the inverter current. Now I'm controlling the inverter current, which is why I am having to see it. Right? The same inverter current if you plotted in the previous case. I would encourage you to do so. So you see here filter capacitor voltages. And you see these are much better, much more relatively smoother. So let's go and zoom in between 0.35 to 0.37. Let's do the same range. .35 to 0.37. So it has done something. Let me go over and let me check. And you see, again, very smooth, balanced sinusoidal waveforms. Alright. So you might actually be wondering what's going on. Let's look at this again. We have this on one side. And we have this on the other. So you might actually be thinking what's going on. If this is the output, if this is the output voltage, why is there input current like this? But that is the entire concept of a higher order filter. Remember I said the inductor itself forms a filter. It's an energy storage element. The capacitor itself forms a filter. It's an energy storage element. These two together form a second order filter. So the inverter current, inductor rather, filters the current but is only able to filter it to a certain extent. The capacitor further filters it and produces a smooth output voltage. This is what is happening. You have a two-stage process, and this is why we are even doing a two-stage process. We are first controlling the current and then controlling the voltage. So now the question is this: how do we know the currents are even controlled? Are they controlled? Well, actually this is not the right plot to look at. And let's go back to the control file and see what's going on and which variables we should plot. Now the current references are set here. I've just set some arbitrary reference, and I would strongly encourage that you try out different parameters. Like you could make this 20, make this 0, make this minus 20, 20, 0. Just play around with different values. Okay, just try it out. And finally, the actual inductor, actual currents D and Q are here. Like I said, we are doing the entire control in the synchronously rotating DQ reference frame. So where are these here? We are storing the D and Q values in these variables, inverter control current D, and we are storing the references in these two variables, inverter control current ref D and current ref Q. So let's plot this. So let's plot each of them separately, because let's plot D separately and let's plot Q separately. So D currents, and here we shall plot inverter current ref D. I shall call this IREF. Save waveform, and then I shall inverter current D, and I shall call this I. Alright, we are done. And let's add the other plot as well. Let's call this Q currents. Let's put IREF Q, let's give IQ, or rather IREF. Save waveform. And let's do I as usual, I. Let's call this done. So now that this is done, let's go plot this one. Let's plot the D currents. And something has happened. Let's go back and check. Alright, so what exactly is happening? Well, what is happening is, actually I plotted the wrong file. Again, it's because of the color coding. You see, orange swamps out blue. So I'm going to flip these two. Alright, let me just delete this plot. Oh, actually I ended up plotting, I didn't delete it. Okay, let's delete this plot. And let's delete this plot. Let's add them again. This time I will add there's just a strange thing with respect to how it's plotted, so we shall add current D to be I, and this will appear as a blue waveform, I hope so, and current ref D, and we call this IREF. And this hopefully will be an orange waveform. So the orange waveform should be somewhere, so should actually emerge out of the blue waveform. I'm hoping. I don't know if that's the case. Let's hope. Let's guess. And let's do Q currents. Again the same thing. Call this I. Save waveform. And these are things that you just learn by trying. I mean, it's not that I've actually I have any rule book or there's any book about how which color will work out. Even I don't know, I'm guessing. Okay, let me plot it again. Let's hope this time we get a plot. Let's go back and let me check. T currents again. And yes, the theory was right. The orange current for some reason is superimposed on the blue. Alright. I think it's something to do with which gets plotted first. So the blue gets plotted first and then the orange gets plotted. So the orange comes above the blue, something of that sort, I guess. But anyway, the orange is the reference, which is 10 amperes. The blue tracks this. You see what's happening? It starts at 0 and then it goes on and tracks it, and it just stays steady here. Now the question you might ask is, why is so much ripple? And the reason is simple, because this is an inverter. You have so much of you have such a large switched voltage. That large switched voltage has to appear as a ripple current here. You don't have a choice. Okay. If you want to reduce this ripple, there's only one possibility, and that is you need to increase the amount of inductor. When you increase the inductor, you increase the filtering power, and therefore you reduce the ripple. So now let's plot the other one, Q currents. And this is Q currents. So Q currents is the same thing. You see here, Q current reference is 10 amperes. It starts at 0, well, almost 0, and then it gradually increases and it starts tracking. Now, if you were to go to basics of control theory, I don't want this. Let me just put these two together. Okay, let me put them together, and that's it. Beautiful. So this is our control result. Okay, so if you go back to basic control theory, what I'm using is a PI controller. Alright, and a PI controller by its very nature can track a DC component with no steady state error. Alright, there is no steady state error. If this was a sinusoidal component, you would see a steady state error, which means a steady state error means, let's say this reference was 10 and it was tracking at 7.5. That's a steady state error. Alright, but that's not the case. You have a ripple above that, but still the average value of this current is still close to 10. So we have zero steady state error. The second thing is, since it is a PI controller, there is some amount of overshoot. You see here there's a hump. This hump is basically when there is an overshoot and it comes back down again. Now, by tuning your PI controller parameters, particularly by increasing Kp and decreasing Ki and increasing Ki, you can reduce this hump such that it is perfectly tuned. Alright, I have not done this and I would encourage you to try it out. Alright, if you do have these files, just play around with the values and see how much you can decrease this and improve the performance. Okay, so as before, I will end this lecture at this point of time. I don't know why it does the resizing. Anyway, at this point of time, I will end this particular lecture because this is what I wanted to show you. So we have covered one part. Before we had done open loop control, which means you were just giving any arbitrary modulation index and seeing what is the output voltage. Now we have been able to control this current and we are able to get an output voltage. Now let's go back and check this output voltage. Now this output voltage, look at the voltage level. The voltage level is less than 150 volts. Okay, this is 150, it's a little less than that, it's a little less, 150 peak. Now these are phase voltages. Okay, this is phase A, phase B, phase C. With respect to neutral, of course it's a isolated neutral, so the neutral is really floating, but it's still there are three single phase voltages. Let's take the regular voltage in North America is 120 volts, 60 hertz. Alright, when I say 120 volts is the phase voltage, or it's 208 volts. Now 120 volts means 120 volts RMS. That RMS voltage multiplied by root 2 will be 170 volts. So we have a voltage, though that it is balanced and sinusoidal, it's fairly sinusoidal, very smooth, and it's also fairly balanced. It is not close to the actual regulated value. The regulated value is somewhere up here. Alright, the reason is simple. We have given some arbitrary currents. We have not given a calculated current. This time we have calculated the modulation index, or rather we have controlled the modulation index to produce a certain desired inverter current. But still there is no control over the voltage. Alright, the voltage is free. And I would suggest another thing. You can play around with these currents. So for example, there is D current and Q current. Okay, I would suggest play around the values of D and Q. Okay, increase them, decrease them, make them negative, positive, zero, everything. See what is the output voltage you get, and you will see that even though you are able to regulate the current, the output voltage is always fluctuating. Alright, the reason is simple. What exactly are we doing in this circuit? We are setting the current through this inductor. Alright, and that current through the inductor sets the voltage, sets the current through the capacitor, which in turn sets the voltage across the capacitor. And when the voltage across the capacitor is of a certain value, that decides the output voltage, output current drawn by the load, because the load will draw current according to what voltage comes across its terminals. Alright, so therefore we are able to regulate up till here, up till the inductor. After this is all free range. We don't have any control over it. It is all incidental. Now in the next lecture we are going to talk about how we are going to regulate the voltages across these capacitors. Alright, because that is the eventual game. This is UPS. Right, we are interested in the output voltage, not the output current, not rather the inductor current. The inverter current is an internal variable. Alright, we don't care about that. The load, what we care about is what the load sees, and the load sees the output voltage. So with this I'm going to end this lecture. As before, let me try to keep these lectures as short as possible. Well, it's actually, this one wasn't that short, but the next lecture, as before, will talk about closed loop voltage control. So if you have any doubts about what I've done, feel free to email me or message me. Otherwise, just wait for the next lecture to come out. So thank you so much for watching, and see you soon. Goodbye for now.